Welcome to this RF Industry Icon podcast. I'm Pat Hindle, and today I'm talking with IEEE Fellow Tsu-Jae King Liu, who is the 2024 IEEE Founders Medal recipient and recognized for leadership in the advancement and commercialization of nanometer semiconductor technologies and the promotion of microelectronics workforce development. And she received this IEEE medal at the prestigious 2024 IEEE Vision, Innovation, and Challenges Summit and honor ceremony earlier this year that I attended. And Tsu-Jae is Dean of College of Engineering and Roy W. Carlson Professor, University of California, Berkeley. So welcome, Tsu-Jae.
Thank you, Patrick. It's a pleasure to join you here.
So I always like to start off with, what inspired you to enter the field? So you received your BS, MS, and PhD in electrical engineering from Stanford. So, how did you get into Stanford and become, interested in electronics and pick that university?
Okay, that's a little bit of a story there. So if you don't mind, let me first explain my background. My father actually studied electrical engineering in college when he was a student in Taiwan. And then he emigrated to the United States where he met my mother, they got married, and I was born in the United States. While he was in the US, he actually switched to applied physics, but he kept in touch with his friends who all majored in EE in Taiwan, and many of them came to the United States, and I got to meet them during their annual reunions, and I learned about I got a sense of what electrical engineers did as a profession. And at that time in the 70s and very early 80s, Silicon Valley was just starting to blossom. So I did get a sense that engineering was a rewarding career, and I had a chance to visit places like the Xerox Palo Alto Research Center. Got to see the very first computer workstation with a mouse and a graphical user interface. So all these things when I was growing up gave me a good impression of electrical engineering. Now, when I was thinking about what to pursue in my own career, I initially, of course, considered medicine, and I found out pretty quickly after about a year or so in school, in college, that I didn't have the stomach for biology, and I didn't like organic chemistry. And so I thought, well, engineers, I know that they build devices that doctors use to diagnose and treat patients. So I thought that engineering would actually be good as an alternative profession to help people. So that's how I ended up majoring in engineering. And I thought electrical engineering because my father and his friends were in that. And also a lot of the friends that I hung out with when I was growing up, playing sports and so on, they're mostly boys. And a lot of them were majoring in electrical engineering. So all of these things gave me some kind of affinity for that field. Now, for my first year in college, I actually went to Caltech in Pasadena, California, and it was a little bit too intense back then. It was 1980. So that school at that time had a ratio of men to women students about 10 to 1, and it was not as balanced. And so I didn't like that atmosphere as well. And so that's why I ended up transferring to Stanford. And I grew up near Stanford, just a few miles away in the town of Los Altos. So again, it was an affinity. I knew that campus very well, and I felt at home there. And so I ended up applying and transferring to Stanford. And at Stanford, at the time they had pretty broad requirements for the bachelor's degree. And when I was getting ready to graduate, I didn't feel like I had enough technical depth to do well as an engineer. So that's why I stayed on for a fifth year to earn a master's degree. And while I was earning a master's degree, I also served as a teaching assistant, and I found I enjoyed teaching. And I also got to learn to meet some PhD students. One of them is my husband today, and he got me interested in research. And so I applied to get into the PhD program. It took a couple of tries, but I was admitted, and that's kind of the history of how I ended up in EE and at Stanford University.
That's a great story. A lot of relationships there, which definitely affect it. So you
Yes.
mentioned the Xerox Palo Alto Research Center, and I think you joined there as a member of the research staff in 1992 for
Yes.
research and development of high-performance thin-film transistor technologies for the flat panel display applications. Can you tell us about your work there and impact on the display technology?
Sure. Well, just to continue my story at Stanford, I ended up doing my PhD dissertation on thin films of a silicon semiconductor alloy called silicon germanium. Actually, germanium was the initial semiconductor that was used to demonstrate transistors, but silicon had some properties that made it advantageous. But alloy silicon germanium had also very interesting properties. You can think of it as combining some of the advantages of silicon and the advantages of germanium. So one of the advantages of silicon germanium is that you can deposit the films and get them to be high quality at much lower temperatures than silicon. And so in the thin film transistor industry at the time, people were trying to figure out how to form high performance transistors on glass for large area electronics applications. So examples of large area electronics are flat panel displays that we all use today in our cell phones and our iPads and in our laptop computers and even our TV screens. Those are flat panel information displays. And each of the picture elements or pixels in a flat panel display is controlled. The brightness is controlled by a thin film transistor, one or more thin film transistors. So back in the early 1990s, companies didn't know how to make high performance thin film transistors on glass, which cannot withstand a very high process temperature. And so my background in low process temperature thin films of high crystalline quality was very conducive to the work that Xerox PARC researchers were doing. At Xerox PARC, you might know Xerox as a copier or printer company, but back then the researchers at Xerox PARC were thinking, with the digital revolution, perhaps paper, which is actually was a big part of Xerox's business, paper might not be the market for paper might not continue to grow if digital displays start to take over. And so that's why they were doing research pertaining to flat panel displays. So at Xerox PARC, I continued to help them advance the thin film transistor technology that is used today in large flat panel like TVs and in your handheld devices, particularly for displays that use organic light emitting diodes rather than liquid crystal display devices. So organic light emitting diodes do need higher performance thin film transistors than liquid crystal display technology.
Yeah, Parker has done a lot of good research. I know they did a lot of metamaterials about a decade ago, and that spun off like 3 or 4 companies in the RF industry. So
Yes.
in 1996, you joined the faculty of University of California, Berkeley. What made you join academia?
Well, as I said before, I found that I really enjoyed teaching. And then I realized I really enjoyed teaching students who are bright and motivated. And so I think it was a good match for me to move to Berkeley. I was very fortunate that they had openings in my particular area of research. At that time in the early 1990s or mid 1990s, the United States, there was still research funding for flat panel display technology. It took a while later for the federal government to decide that they would just rely on flat panel displays manufactured outside of the US. So they didn't want to invest much further in domestic research on this topic. So I moved to Berkeley because I knew that I enjoyed research, but I loved to teach. And yeah, I was just fortunate that it all worked out.
And then I think you founded Prognoscent Technologies. Can you tell us about that company and its technology?
Sure. So Progressive Technologies was just a small startup company started by my husband and myself. My husband's area of expertise is similar to mine in solid state devices or semiconductor technology. And his area of expertise was at the time, was in non-volatile memory technology or flash memory technology. So flash memory devices, each memory cell or that stores 1 bit of information, actually more than 1 bit of information, is really just a transistor, but the transistor has a floating electrode embedded in it, so you can store charge on it to change the threshold voltage, the voltage needed to turn on and off that transistor. And I was doing research at Berkeley on just ordinary transistors, and some researchers had published that if you can get a transistor to turn on, well, ordinarily to turn on a transistor, you apply a voltage, and the voltage that the transistor conducts current, the two terminals between which the transistor conducts current, that also has a voltage applied. There's also a voltage that's needed to get the transistor to conduct current. So there were some researchers that published papers showing you can actually implement much more compact digital logic circuits and memory cells if you can design some solid state device that turns on with increasing voltage, but eventually starts to turn off with increasing voltage. So that piqued my interest. And my husband and I were discussing this. This is a device that turns on as you increase voltage and turns off if the voltage is too high. That is actually like a non-volatile memory device, because that's how you program a non-volatile memory device to change the threshold voltage so that it turns off. So then we thought, well, what about making a non-volatile memory device volatile? Like you have it turn on and off just instantaneously as you change the voltage back and forth. And so that kind of a device actually was exactly what the researchers had published would be useful for implementing compact digital memory and logic circuits. So then we wrote up some patents on the idea. We worked with a really talented patent attorney and developed an IP portfolio. And then we shopped it around, and that we did get an offer from a VC, but we also got an offer to be acquired by Synopsys, which at the time was trying to build up its intellectual property portfolio. And so since we had a young family with two young children, we thought it'd be better for our family if we were acquired rather than to really go with a full-fledged startup company. So that's how I ended up working at Synopsys, because they acquired Progressive Technologies.
And so you spent, I think, 2004 to 2006 as the senior director of engineering in the advanced technology group at Synopsys. And so did you continue your work or did you work on something else?
Yes, so Synopsys brought resources to bear on this intellectual property. And so we did run some experiments with some semiconductor companies and got some experimental results. The results showed that the idea worked, but for high performance static memory or SRAM applications, we needed to have a much better performance than we were able to achieve with the initial experimental results. So we ended up deciding not to pursue that technology any further, but instead I pursued some other new interesting transistor designs and continue to advance Moore's law. It's a little bit more traditional, but something that the industry could benefit from more immediately.
Yeah, so you're very well known for your development of polycrystalline silicon germanium thin film technology for applications in integrated circuits. So can you tell us about, that work and its applications as you further the technology?
Sure. So when I was a PhD student, one of the applications I investigated experimentally was tuning the content of germanium in silicon germanium to tune its electrical properties. And it turned out that at the time, polycrystalline silicon was used as the gate electrode material in all digital integrated circuits. And so I showed that if you incorporate germanium into that polycrystalline gate material, you can actually tune the electrical properties and actually tune the threshold voltage, the turn-on voltage of the transistors. The threshold voltage of a transistor is critical to control during the manufacturing process because if you have a low transistor threshold voltage, then that's good for high performance, but it's not good for low power operation. And if you increase the threshold voltage of a transistor, that's really good for low power operation, but not good for high performance. So to tune the trade-off between high performance and low power consumption, it's critical to adjust the threshold voltage. And so polycrystalline silicon germanium gate electrode technology gave the industry a means for tuning the trade-off between high performance and low power. And actually, in more recent years, the industry has developed similar other other gate electrode materials that also have tunable work function. And those are actually used today in high volume production for integrated circuit chips.
Very interesting work. And then you also did work with FinFETs. Your contributions there drastically improved the speed and functionality of semiconductor circuits and have extended the life of Moore's law, as you were discussing. Can you tell us about your work with FinFETs? What led up to the development of that? Because it really dominates some of the semiconductor technologies today in the high performance market.
Yes, so I was very fortunate to have outstanding colleagues to collaborate with at Berkeley. So Professors Chen-Ming Hu and Jeff Boker, we had some funding from the Department of Defense, DARPA. At the time, there was a program called the Advanced Microelectronics Program, where the program manager was challenging researchers to come up with a transistor design that could be scaled, miniaturized to much smaller dimensions than conventional transistors at that time. So in the late 1990s, the most advanced technology used quarter micron or 250 nanometer long gate length transistors. And so the challenge for the advanced microelectronics program was to demonstrate transistors that can function well at 25 nanometer gate length. And that was 10 times smaller than the state of the art. And we ended up, because it was a fantastic team of researchers from around the world that came and worked together on this, we demonstrated transistors functioning very well, well below 25 nanometers in gate length. But it's a huge collaborative effort. Lots of hardworking visiting industrial fellows and graduate students and postdocs that contributed to that work.
And so today you're at UC Berkeley. What are you working on now?
So today, with the advancement of semiconductor technology enabled by FinFET, right? So FinFET, the fin-shaped transistor, has enabled the industry to scale the gate length down well below 25 nanometers. It's below 20 nanometers today. It's become apparent as electronics have proliferated and enabled the AI revolution that there's always going to be more demand for computation and memory. And now what's become very apparent is the energy consumption of computing. So just this week, there were a couple of announcements, high-profile announcements of some major cloud service providers, Google and Amazon, that they're partnering with manufacturers of nuclear power plants, so that they plan to use nuclear power to power data centers in the future, because they can easily consume 100 megawatts or even more of electricity. And so for the researchers, we see the trend of AI and other applications of electronics continuing to grow. So we really need to find ways to dramatically improve the energy efficiency of computing. And so my research for the last more than 10 years has been focused on new solid state devices and chip architectures that will enable orders of magnitude lower and power consumption for computing. In other words, increasing the energy efficiency of computing by many orders of magnitude.
What are some of the ways that you're investigating to lower the power?
Well, there's new chip architectures. So a lot of the energy needed to perform computations, let's say for machine learning, you need to process lots of data. So one way is to actually perform the computation on the data where it is stored in memory. So this is in-memory computing. So my group has been looking at innovating some devices that can facilitate in-memory computing, but also for a wider range of applications. For example, if we want to be operating in space, right, near Earth orbit, then the devices not only have to be energy efficient, but they also have to be relatively low cost. They have to operate in a wide range of temperatures, cryogenic to very high temperatures, and they have to be radiation hard, right? They have to be able to withstand high energy particle irradiation. So my group actually has been working on mechanical switches. So if you look at the history of computing over the last 120 years, in the early 1900s, electromechanical switches were used for digital computing. And we're revisiting that using state-of-the-art manufacturing technology that's used for transistors. If we can make mechanical switches just as small as transistors, it turns out they become more energy efficient, even more reliable, and certainly radiation hard and temperature tolerant compared to transistors.
Oh, that's very interesting. So I thought I'd shift gears and talk about, how you initiated many successful programs to increase diversity and equity in the field. And this includes the Rising Stars and EECS workshop at UC Berkeley, which helps women become professors. And, where does the industry stand at this point with diversity success? What does it need to do to get to the level that you think would be optimal?
Well, that's a loaded question. Ideally, since engineers design and build devices, systems, processes that are intended to benefit people in society, and women comprise roughly half of the people in society, I think it is important to make sure that engineering teams who are going to shape our future do include a proportionate number of women. So this is why I think it is important to ensure to attract and support women to pursue careers in engineering. And so one way to do that is to show women that it is actually a welcoming and inclusive profession. And so that's one tack. And to give people confidence that women can succeed in the field. So highlighting successes of engineering teams that include women is one way. And if there are women who have actually been very successful as leaders in engineering teams or of tech companies, it's also good to celebrate their successes so that young students, men, both boys and girls, can see that women can contribute and make a positive difference in the profession and with positive impact on society. I think the key is to make it clear to the general public that women have and will continue to contribute to advancements in technology and to provide mentorship and other types of support to ensure that students, both men and women, succeed. I think if things we do to help women succeed also benefit men. One reason why women in college might not be as well prepared to pursue engineering is because maybe they weren't encouraged before to take a lot of math and science courses or to excel in math, science, and computing courses. We have boys or men entering college who also, for whatever reason, did not get as much experience, hands-on experience with math, science, and computing. So if we have programs that support students who don't have that experience coming into college, it can benefit both men and women. And I think in the end, it benefits our society.
Oh, you've done some excellent work there. So we congratulate you on that and hope you continue. So you've authored or co-authored over 500 publications and you hold over 90 patents. What work do you consider the most important, like to the industry and its future?
Well, clearly, so far, the most impactful work has been the FinFET because there's so many devices that people use today that actually have FinFETs in them. But I do think it will take time. But some of the other innovations, including mechanical computing technology, I think eventually we'll find practical applications in society. But I think one of my biggest contributions, actually the biggest contribution that I've made to the field and to society is actually through my students, right? The students I teach have taught in the classroom, the students I've mentored in research, they go on and do so much more than I could ever do myself.
Yeah, it's good to be such a great influence on so many people. It's definitely a great endeavor.
Yeah, it's very rewarding.
So I have to ask you, is Moore's Law going to continue? That's always a question that everybody debates about. How do you see the future of semiconductor technology evolving, say, over the next decade or so?
So Moore's law will definitely continue, but it's evolving. It already has evolved. So Moore's law traditionally is talking about the number of components, transistors that you can fit into a single chip. And today, Moore's law has evolved to be the number of transistors you can package together in a integrated circuit system. And so we see today that the industry has continued to increase the number of transistors in a package and is projected to reach 1 trillion transistors in a package by the year 2030. So it's still maintaining that exponential growth in complexity of integrated systems, and this will benefit the capability in terms of the capability of computing devices in the future. But we have to move to packages of chiplets, small chips that are packaged very tightly together. And this is enabled by advancements in chip packaging technology. It just turns out that economically, it turns out to be more cost efficient to tightly package multiple chiplets together rather than fabricating the whole system on a single chip, a large chip. And that's because the wafer size is not changing. So if you have large chips, then you have fewer chips per wafer. And if you have a defect that kills one chip, then your manufacturing yield drops dramatically if you only have like 10 chips on a wafer. But if you have 100 or 1,000 chips on a wafer and you lose one, then the manufacturing yield is still very high. So it's more cost effective. So enabling the industry to make advancements by making smaller chips That's the way that Moore's law has evolved, and I do think that we'll continue to see exponential improvements in computing technology in the years ahead.
Yeah, I've always agreed that, we're packaging, we have 3D packaging, and we'll find more creative ways to put things together. It's amazing how big a chip has gotten that we have to now slice it up into chiplets to make it work.
Yeah, to make it cost effective to manufacture. Yes.
Well, thank you so much, Tsu-Jae, for the talking with me today about your career. It's been a very rewarding career. You've had a big effect on the field, so really appreciate you taking the time to talk to me today. You're definitely an icon in the field of semiconductors, and thank you so much.
Well, thank you so much, Patrick, for spending time with me. I really appreciate your interest, and hopefully our conversation will have impact on the future generation of engineering leaders. Thank you so much.
To our audience, you can find more podcasts at podcast.microwavejournal.com. Thanks for listening.